So welcome to the first video on classical mechanics. And in this video, we're going to talk about the different coordinate systems that arise in our discussion of classical mechanics. And those three or four are Cartesian, polar/cylindrical, and spherical coordinates. Now, you are already probably familiar with these different coordinate systems, but I encourage you to continue to watch through it because there are some topics that you probably haven't seen before that will be discussed in this video, such as analyzing special angles or acknowledging the fact that some basis vectors are dependent on the location of the point that you're describing. So the first one we're going to talk about is Cartesian coordinates. Another name for this is the rectangular coordinate system. And this one's pretty straightforward. We're going to have three axes, all perpendicular to each other, c, x, and y. And we're going to have a point P in space somewhere. And P is going to have coordinates x, y, and z. So x, y, z. And I'm just dropping down some projections onto some axes so you get a better idea of what these coordinates look like. So this is the x-coordinate, this is the y-coordinate, and this is the z-coordinate of P. Now, we also can give this coordinate system some basis vectors. I'm already assuming that you know what a basis vector is. It's just a vector that has magnitude 1 that points along a given direction. And the directions in these cases are the axes of the coordinate system. Then we can draw a vector from our origin right here, we'll call O, to point P, and we'll label it OP. Now, I know you're used to seeing maybe an R or maybe a script R, an S, stuff like this, but we're going to use a more descriptive position vector notation, and that's going to be OP. The vector ends at the point P and begins at point O. And this is because later on we're going to start dealing with vectors that don't necessarily start at the origin, and so it just makes things a little bit more clear. And if P has coordinates x, y, and z, then OP can be written as x in the x hat, plus y in the y hat, plus z in the z hat. And this is the position vector of point P relative to the origin O. That's why this notation is very descriptive, very useful, because it tells us that it's the position of point P relative to our origin O. All right. Now, there's a note here. Something to keep in mind is that the basis vectors do not depend on the location. Basis vectors do not depend on location of P. That is, if I were to instead choose a new point down here and call it P, right, then OP, oh, that's not very straight. OP can still extend here, right? But the basis vectors, none of them moved. They all stayed exactly where they're at. This is not going to be the case with polar and spherical coordinates. And luckily in Cartesian, this makes taking derivatives of, say, if I want to take it with respect to time, right? This makes taking these derivatives a lot easier because we only have to differentiate the components, dx dt and the x hat, plus dy dt and the y hat, plus dz dt and the z hat. However, if x did depend on the location of P, then when we start talking about things like displacement, then the basis vectors would also change with time, as we'll see with polar. All right, so moving into polar coordinates, instead of describing the location of our point P with three coordinates x, y, and z, we're instead going to use three coordinates r, theta, and z. So I have my point P here. I can drop its projection down into the xy plane, so this is still z, x, and y. But we're instead going to describe it with a radial coordinate that radiates from the origin, we'll call it r, and a theta component, an angular component, that goes counterclockwise from x to y. It's not a very good x. And also a z component right here. And so P has components r, theta, and z. It's very important here to note that r can take any value 0 to infinity, right? R can be any value 0 to infinity, and theta can take any value 0 to 2 pi. It doesn't matter which one you include, by the way. I like to actually include 0. Right? All right, now a good question to ask is how exactly do we convert from Cartesian to polar coordinates? And the answer is quite simple. So I'm going to look at a 2D projection here. So I'm going to assume that our particle's in the xy plane, y and x, and I'm going to have a point P here. So here's our radial coordinate, r. I'm just going to make that bigger, and then we have an angle theta. Now you could use trigonometry here, but instead we're going to use a trick that's going to come up a lot more in this class, and that's by analyzing special angles. We're going to determine this, or sorry, I can't speak. We're going to determine the conversions by analyzing special angles. So a good question to ask is, what happens when theta is 0 degrees? Well, if theta were 0 degrees, you can see that this r, right, will lie entirely on the x-axis. So this tells us that r is equal to x. But what if theta were 90 degrees instead? Well, this tells us that r is going to lie entirely on the y-axis, right here. And so r is y. Now, all we need to do is multiply r by necessary or appropriate, that's the word I'm looking for, by appropriate trig functions to figure out what the conversions are. So here we have that x is r and y is r. But when is x r? X is r when theta is 0 degrees. This tells us that x is actually r cosine of theta. Because if theta were 0 degrees, then x is equal to r. And if theta were 0 degrees, y has to be 0. And the only way that can be true is if y is r sine of theta. But these are also true for theta is 90 degrees. If theta were 90 degrees, then x is 0, and y would be r. And we know that to be true from our analysis up here. If theta were 90 degrees, then r would lie entirely along the y-axis, no x component. Cool. Pythagorean theorem tells us that the square of the hypotenuse is x squared plus y squared. And because r is always positive, it only goes from 0 to infinity, we know that r is the square root of x squared plus y squared. Also, if we take y and divide it by x, we're going to end up with tangent of theta, right? Because we're going to have r sine of theta in the numerator and r cosine of theta in the denominator. R's cancel out, and we're just left with tangent of theta. So we have that theta is arctangent of y divided by x, assuming x does not equal 0. Cool. So here we have some relations. We have x and y to r cosine of theta, r sine of theta. We have an expression for the length of the radial component, and we have a value for the angular component. Cool. Now, just like with Cartesian coordinates, we can describe the position with a vector. So this tells us that we also need to have some basis vectors. And these basis vectors are going to be z hat, just like Cartesian. We're going to have a r hat component that points in the same direction as our radial vector, and a theta hat component that points in the same direction as our angular component. And in 2D, that just looks like this. We have r, that's not very straight, but r and theta. Now, these basis vectors are also mutually orthogonal to each other, just like with Cartesian coordinates, which tells us that if I want to get a different color here, if I looked at r hat cross theta hat, I know that this has to equal z hat. And theta hat cross z hat must equal r hat. And by the way, also z hat cross r hat will give us theta hat. A good trick here is to memorize these, is the circle of doom. That's how I learned it in calculus. And that is, you take your basis vectors and you draw them in a little circle. So we have r hat, theta hat, z hat. And if you go clockwise around this circle, so theta hat cross z hat, it's going to give you positive the next one. So this is r hat. But if you go counterclockwise, let me erase this real quick. If you go counterclockwise, let's say z hat cross theta hat, right? This is going to give you the next one with the minus sign. Cool. And this is true for any set of basis vectors that are mutually orthogonal to each other. and are normalized. All right. So if we draw a vector from our origin, which is right here, to the point, we see that this vector gets broken into a radial component, so r in the r hat direction, and then a z component, z in the z hat direction. So our vector OP is clearly r in the r hat direction plus z in the z hat. And if this were in 2D, OP would just be r in the r hat direction. Now, unlike with Cartesian coordinates, these basis vectors do depend on the location of the point P, right? If I drew P, say, right here instead, right? So our vector OP would go here, right? But what would our basis vectors look like? Well, r hat would point this way, right? And theta hat would point this way, direction of increasing angle. You can clearly see that the direction that these point are not the same direction that these point. And so we can conclude that the basis vectors do actually depend on the location of P. This is going to be very important when we start deriving velocities and accelerations. Right? So let's move into spherical now. Spherical coordinates. This one's a bit more nuanced, but it's also kind of fun because we can use our special angles again. So here, what we're going to have is a sphere. And we're going to stick some axes on. I don't really like those axes. Draw like this maybe. So z, x, and y. And we're going to have a point P. Okay. Well, we can actually describe the location of this particle with a, I'm going to use blue here, with a radial component we'll call r. Some texts call this rho. Every math book that I've seen calls this rho. I still like to call it r. And then a theta component that goes down like this, call it theta, and then an azimuthal component, or a horizontal angle, phi. I actually like to draw my phi's like that. It's important to note that r can take on any value, 0 to infinity. The sphere can have infinite radius. Theta can only take on values 0 to pi, because if you think about it for a second, this can only go down to here, right? Technically, it could go all the way around, but if it did go all the way around, then it'd be no different than the azimuthal component phi. It'd be the same. Phi can take on any value, 0 to 2 pi. And with these domains, these three coordinates can describe an entire sphere, the surface of an entire sphere. Okay. Oops. So P has components r, theta, and phi. All right. But what are the conversions from Cartesian to spherical? Now this one is a little fun, but it's a little nuanced, so I'm going to take a few steps here. So first, let's look at x. So we're going to look at x. All right, I'm going to go ahead and redraw this. Just a very simplified version. All right. If this is my point P, I'm gonna draw this a little bit bigger. Oops. Okay. It looks like the same size actually. It's fine. So here's my point P. Here's R. Right? And if this is Z, X, and Y, all right, to find the x component, we need to force x to be equal to r and then tack on some trig functions, the same way we did it for polar coordinates, right? So in order for x to equal to r, we need to first take this r and force it to be in the xz plane. That's the first thing we need to do. And the way we do that is by setting phi, this angle here, equal to 0 degrees. So phi must be 0. And when that's true, right, x is now, or r, sorry, is in the xz plane. And then if theta goes down like this, right, we force theta to be 90 degrees. And if this is true, right, so we take r, we take our r, we force it to go this way by making phi 0 degrees, and then we take it and we force it to go down, laying down like this. So phi becomes 0 degrees, theta becomes 90 degrees, and then r lies along this x right here. So this tells us that x must be r sine of theta cosine phi, right? Because if phi were 0 degrees, then we're left with x is r sine of theta. And then when theta is 90 degrees, we're left with x is equal to r, right? Now, now suppose we wanted y, right? Y instead. Well, to get y is equal to r, right, we need phi to be 90 degrees, right? We want phi to go all the way into the zy plane, right? This picture kind of depicts that really nicely. And then we want theta to go down 90 degrees again, just like with x. So theta is 90 degrees. So again, phi goes 90 degrees. It's now in the xy plane. And then theta goes down 90 degrees. And now it's lying along this line. So we have y is r sine of theta sine of phi. Cool. Okay. Now, z is a little tricky. It's also the easier one to think about. Just a little trick here. If p were over here, for example, right, and their z components were the same, right, we can clearly see, so their z components are the same, we can clearly see, right, that there is no phi dependence. If I were to draw a little circle here, make things, actually I'm not, that's going to make things a little convoluted. If I were to take this r, and I were to force it to go anywhere around in a circle, right, the z component of that vector, quote unquote, is going to be the same. So it does not actually depend on what phi is. However, in order for this vector to lie along the z-axis, vector, quote unquote, we need theta to be 0 degrees, lining up the z-axis. So z is r cosine of theta. And there we have it, the 3 conversions from Cartesian to spherical. And of course, r in this case is x squared plus y squared plus z squared. This is a fun exercise to go through on your own. You can use Pythagorean theorems twice, once in the plane and then once in another plane, to determine this relationship here. Sorry, it's r squared. Cool. Now I'm going to go back to my picture here. Just like with polar and Cartesian, we can of course describe the location of p with a vector. So we're going to tack on some basis vectors. And here I'm going to use a deep purple. So r is obviously going to go out, r hat, just like with polar, just radially outwards along the r direction. Because theta increases this way, phi hat's going to go this way. And then phi hat is going to go out this way in the direction of increasing phi. That is a loud car, I'm sorry about that. So r hat, phi hat, and theta hat. And of course, these are mutually orthogonal, so you can throw them into your basis, your circle of doom, and get the relations that you need via some cross products. So anywhere we see an r hat cross a theta hat, we get a phi hat. If we see a phi hat cross a theta hat, we know we get a minus r hat. Right? And with this, we can see that our vector, OP, is just equal to r in the r hat direction. It's very simple. All right, that about does it for our different coordinate systems. Cylindrical and polar. The 2D case of this is what people typically call polar. I'm going to refer to it as polar/cylindrical throughout the entire course as the same. There's not really a distinction in my eyes. I know that's probably making some of you shake with anger, but apologies. So yeah, I highly recommend you go through these derivations and you make sure what the basis vectors are, what the components are, and being able to convert between these different reference frames. Practice your special angles. That's going to come up everywhere in this course, especially when we start looking at force diagrams. Oh, one more thing before we end this video. Of course, just like with polar, the basis vectors in this reference frame are dependent on the location of p, right? Say p was over here, then r is going to point out this way. Theta is going to point this way, theta hat, and then you can imagine phi hat coming out the board thus. Yeah, but they do change depending on their orientations change depending on where P is. All right, that about does it. I'll see you in the next video. In the next video, we're going to derive velocity and acceleration for these different coordinate systems, which is it's a bit involved, but we'll get through it. Thanks.